All right, next up we have change in free energy. Symbol for change in free energy is delta G. So it's also called Gibbs free energy, Gibbs. Delta G, and we're going to use delta G to determine or predict if a reaction is spontaneous or not, or thermodynamically favored or not. So it says free energy is the maximum magnitude of useful work that can be obtained from a reaction. So really not that significant. Again, the significance of delta G is it will tell us if a reaction is spontaneous or not. So there's a couple different ways we can calculate delta G. We talked yesterday about the factors that affect the spontaneity of a reaction, those being the enthalpy factor or delta H and the entropy factor or delta S. So this first equation shows the relationship between delta H and delta S and how they ultimately affect delta G. So here it goes. Delta G naught technically is equal to delta H naught minus T delta S. All right, looks like I'm out of room a little bit here, so let me erase that and I'll fill in this part of the notes. All right, so change in free energy of the system, that's our delta G. Make notes that delta G is often expressed in kilojoules per mole. So as we'll see in a little bit, technically the sign for delta G tells us if a reaction is spontaneous or not. Change in enthalpy is represented by delta H. This is also in kilojoules per mole. And then the change in entropy, that's our delta S, which is in, be careful, joules per mole Kelvin. So when we plug in a value for delta S, we need to first convert that to kilojoules per mole Kelvin. And then, of course, T is our Kelvin temperature. All right, so here's how it works. When delta G is negative, that means that the reaction or process is spontaneous or thermodynamically favored, where the products, that whole thing should be underlined, I guess, the products are favored. Conversely, when delta G is positive, that tells us that the process is non-spontaneous, meaning the formation of products will not occur by itself because the reactants are favored. Another way of calculating delta G, besides using delta H and delta S, is by using the delta GFs of the substances involved in the reaction. So much the same way that we use delta HFs to calculate delta H for a reaction, we can calculate delta G for a reaction using delta GFs. So just like before, we got formation reactions where you have elements combining to make compounds. Again, formation of 1 mole of a compound from its elements in their standard states. So just like with delta HF for elements, the delta GF for an element is 0. So the only other thing that's not always 0 then is going to be S for a substance. That's not 0. But delta HF for an element, delta GF for an element is going to be 0. All right, formula, again, technically this is at standard conditions. So let's add those. Delta GFs of the products minus delta GFs of the reactants is going to give us delta G for the reaction. So I don't know if you noticed already in that table in the back of the book, you have delta HFs, you have absolute entropies, and you have delta GFs. We're going to use those values. All right, take a look on page 588. Diatomic nitrogen and oxygen molecules make up blah, 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 whatever. Evaluates delta G for the following reaction at 298 Kelvin using delta GF values from the appendix. And then once you get the answer for delta G, determine if the reaction is spontaneous or not. So there's the equation for the reaction. So delta GFs of the products, again, we're going to multiply delta GF of NO by 2, since there's 2 moles formed according to the equation as written, minus the delta GFs of nitrogen and oxygen, which of course are both 0, so we don't really need those. And we get a delta G for the reaction that is positive 173.1 kilojoules per mole of reaction. Given that delta G for this reaction is positive, that tells us that at 25 degrees Celsius at least, that this reaction is non-spontaneous. So going back to this equation, we'll talk about in a little bit. Not only does delta G depend on delta H and delta S, but sometimes depends on temperature as well. So that's why it's given in the problem that at 298 Kelvin at least, this reaction is non-spontaneous. Thermodynamically not favored, or not thermodynamically favored is probably a better way of saying that, or also endergonic. So we have endergonic and exergonic. So those are not exo, but exergonic, endergonic are also terms that we may see. But usually it's thermodynamically favorable or not thermodynamically favorable, or spontaneous, non-spontaneous. All right, so there's an example in your book on page 600, number 111. Let's go ahead and do all 3 of those. Use the delta GFs from the back of the book to calculate delta G for each of those reactions. And like the example problem, once you get delta G, indicate if that reaction is spontaneous or non-spontaneous at standard conditions. Go ahead and pause now. Alrighty, here are our answers. So for letter A, we get 8.3 kilojoules per mole. That tells us that this reaction is non-spontaneous at 298 Kelvin. Same thing in letter B, 5.3 kilojoules per mole, non-spontaneous. And then letter C, negative 364.0 kilojoules per mole, negative delta G, which indicates that this reaction is spontaneous at 298 Kelvin. In fact, maybe you already knew that. When you take sodium metal and you put it in water, a reaction occurs. And so, given that a reaction occurs, that means this reaction is spontaneous. So, makes sense then that delta G that is calculated would be negative. Now, the other 2 reactions maybe are less familiar, and so obviously if it's not a familiar reaction, you won't know if it's spontaneous or not until you calculate delta G. All right, let's take a look at the next one. So read along the bottom of the page. Make the same determination as in the last example, except this time using, instead of delta GFs, we're going to use heats of formation and absolute entropy. So this time we're looking to use this equation. And since we're using delta HFs and delta S's from the back of the book, those are at standard conditions. Our temperature here is going to be 298 Kelvin. So just be careful that a couple students have asked about the significance of this little knot or degree symbol and implications of that on calculations, and the only implications are right here, because the problem doesn't say that the reaction occurs at 298 Kelvin, but again, we're assuming, since we're calculating delta G naught, that the reaction occurs at standard conditions, so 298 Kelvin for the temperature. So take a look at the solution. It's nothing really new. Use delta HFs to calculate delta H. So delta H for this reaction is 180.5 kilojoules per mole. Calculate delta S using absolute entropies of the substances involved in the reaction, and we get 24.9 joules per mole Kelvin. So we got to convert that to kilojoules per mole Kelvin. So do that multiplication first. Do 298 Kelvin times 0.0249 kilojoules per mole Kelvin, and then subtract that from 180.5 kilojoules per mole, and we end up with an answer of, once again, 173.1 kilojoules per mole, just like what we got in 1519. All right, page 600, number 112. Same thing you did in, or same reactions as number 111, but this time use delta HFs to find the delta H for the reaction, and absolute entropies of each substance to find the delta S for the reaction, 298 Kelvin. You know what? Just to save a little time, let's do letter A only. I think we don't have to do all three of them. Do letter A, and then compare your answer that you get in with that, what you got in number 111. All right, go ahead and pause the video now. So again, negative 71.8 kilojoules per mole for our delta H for this reaction. Negative 268 joules per mole Kelvin. So notice we have an exothermic reaction, which is favored in nature, so exothermic. That decreases in entropy, so delta S is negative. Again, most exothermic reactions are spontaneous, but we can't just look at the delta H or enthalpy factor. We must also consider the entropy factor. So in this case, it looks like entropy rolls out because this reaction is non-spontaneous. So a little different answer than what you got in 111, maybe rounding or just some other values there that's caused it to be just off from what you got in 111, which is okay. All right, which brings up our next topic, which I kind of alluded to already, is that sometimes, like in that last example, the spontaneity depends on temperature. So we have an exothermic reaction that decreases in entropy. Ultimately, then, the temperature at which that reaction occurs will determine if it occurs spontaneously or not. So something to keep in mind is, let's say you have a reaction that's at equilibrium. Forward reaction and reverse reaction are both occurring spontaneously. That's weird, isn't it? How can the delta G for the forward reaction and the delta G for the reverse reaction both be negative? Well, they're not really negative, I guess. So at equilibrium, delta G for that reaction is 0. Now take a look on page 586. Actually, no, I don't want you to look here yet because this is something we're going to kind of go through and derive. So don't do that yet. Don't peek. We'll take a look at something very similar to that, and we'll use an example to help you really understand how temperature affects spontaneity. So let's again skip ahead then to the derivation of a formula. So at what temperature, or better yet, as we'll see in a little bit, above what temperature or below what temperature is a reaction spontaneous? So let's start off with this equation. And let's say we have at equilibrium, so our delta G is 0. So we have delta H minus T delta S. And let's go ahead and subtract delta H from both sides. So we get negative delta H equals negative T delta S. And then I'm going to divide both sides by, I guess, negative delta S. And so ultimately, we end up with this. So if we take the delta H for a reaction and divide it by the delta S for the reaction, we'll calculate the temperature at which that system is at equilibrium. Better yet, we can determine then the temperature at which that substance that reaction occurs spontaneously. So either above that temperature that's calculated, depending on the situation, as you'll see in a little bit, or below that temperature. In fact, let's think back to Chem 1. Remember that we talked about the reactions that are sometimes spontaneous? Right, this reaction is sometimes spontaneous. For example, exothermic reaction that decreases in entropy, both delta H and delta S are negative. That reaction is sometimes spontaneous. When is it spontaneous? Well, at some lower temperature. Lower temperature, what the heck does that mean? Lower than what you would calculate here. Or sometimes reactions are only spontaneous at some higher temperature. Higher temperature, what does that mean? Well, higher than what you would calculate by taking the delta H for that reaction divided by delta S. All right, go to 589. Let's take a look at that example there, 1521. So it says use thermodynamic data in Appendix K to estimate the normal boiling point of bromine. Assume that delta H and delta S do not change with temperature. So kind of the same thing here. We're going to plug in, turn the page in the book. We're going to plug in the delta H for the reaction and plug in the delta S for the reaction, divide those. And notice because delta S has units of kilojoules per mole Kelvin, when you calculate T, that's going to be in Kelvin. So we get 332 Kelvin or 59 degrees Celsius. That is the temperature at which the change from liquid to gas for bromine is at equilibrium. So boiling point, we have both ways, liquid to gas, gas to liquid occurring at the same time. All right, now let's go to page 601, number 121, same idea. This time though, we're going to calculate the normal boiling point of pentacarbonyl iron, FeCO5, at 1 atmosphere. So go ahead and use the values from the back of the book, the delta H, heat of formation, and the delta S, or conversion of rather liquid to gas values, delta S for that, and calculate T. Go ahead and pause the video now. So using delta H for change from liquid to gas for that substance, we get 40.2 kilojoules per mole. And then delta S for the change from liquid to gas, 107.2 joules per mole Kelvin, or 0.1072 kilojoules per mole Kelvin. We get 375 Kelvin, which works out to be 102 degrees Celsius for the normal boiling point of that substance. All right, so now if you want to go back to 586, that's fine, but I'm going to walk you through. Let's build a table. Different values for delta H, sorry, different signs for delta H, delta S. And then I'm going to add a column there. Let's add delta G, and then the spontaneity of the process. So let's start off with processes that are favored in nature. Any process where what you end up with has less energy than what you started with is favored in nature and is likely to occur spontaneously. So we're talking about exothermic reactions, delta H negative. And a process that increases in disorder. So what you end up with has more disorder than what you started with, so delta S is positive. If delta H is negative and delta S is positive, well, let's go back to this equation. If delta H is negative, whoops, and delta S is positive, then that means delta G is going to be negative, no matter what the temperature is. Doesn't matter for T here. So minus a plus, we get a minus. And so we'll say that this kind of process is always spontaneous. Again, meaning no matter what temperature the reaction occurs at, it will occur all by itself. Let's look on the other way. How about an endothermic process, not favored in nature, that decreases in entropy, also not favored in nature. So if our delta H, let's erase this here. If our delta H is positive and our delta S is negative, what is the sign for delta G? Well, minus a minus is a positive, so that means that delta G is going to be positive in this case. And so what we would say here is that this kind of process, this reaction, is always non-spontaneous or never spontaneous. Again, meaning no matter what temperature this reaction occurs at, it will not occur on its own. All right, how about a process that is exothermic, so delta H negative, that decreases in entropy. So minus minus. So let's take a look there. So delta H negative, delta S negative. What is the sign for delta G? Well, in this case, it depends on the magnitude of delta H compared to the magnitude of T delta S. Now, speaking of magnitude, the magnitude of T delta S ultimately is determined by the magnitude of T. So now, when can delta G be negative? Delta G will only be negative if the magnitude of T delta S is smaller than delta H, because then we're going to have a bigger negative number here, say, than here. So if you had negative 100 minus negative 50, you get negative 50. So notice that T delta S is smaller than delta H. So I'm going to put that there, meaning it depends. The sign for delta G depends ultimately on temperature. So this time, again, we're going to say this process is sometimes spontaneous, and it will only be spontaneous at some lower temperature. Low enough, and we already talked about how to calculate that temperature. Temperature lower than what was calculated, say, in this problem here. All right, we got one more. Endothermic process, not favored. Increases in entropy is favored. Sign for delta G, don't know. So let's look at this situation. Plus plus, delta H, delta S. And then keep in mind the sign for delta S is the same as T delta S, since T is in Kelvin. All Kelvin temperatures are positive. So in this case, what would be the sign for delta G? Well, it would be positive. That's non-spontaneous. How about now? So in this case, in this situation, endothermic reaction that increases in entropy will only be spontaneous if the magnitude of T delta S is greater than delta H. And when is that? So let's write here. So again, sometimes spontaneous. This time only spontaneous at some high enough temperature, making T delta S bigger than delta H. All right, let me give you an example of this. And this is what's on page 586. Let's consider the process of melting ice. First of all, what number is this we're talking about? 1, 2, 3, or 4? Well, melting is endothermic, so it's got to be either 2 or 4. Melting involves changing from a solid to a liquid, so that involves an increase in entropy. So we're talking about number 4. So the question is, does ice melt spontaneously? Will ice melt all by itself? If you said yes, then I'm going to say, really? So ice inside your freezer melts all by itself? No. If you said no, I'm going to say, really? If you take ice and put it on the counter, it does not just turn into liquid all by itself? It does. So what determines if ice will melt spontaneously? The temperature. So at any temperature above 0 degrees Celsius, ice will turn into liquid water all by itself. So outside of the freezer, melting is spontaneous. Inside the freezer, where the temperature is less than 0 degrees Celsius, non-spontaneous. Let's try one more. How about freezing of water? First of all, freezing is exothermic, so either 1 or 3. Freezing involves changing from a liquid to a solid, so we have a decrease in entropy, so that would be number 3. Does water freeze all by itself? If you said yes, then I'm going to say, really? Water just sitting out on the counter is going to turn into ice all by itself? I don't think so. If you said no, water does not freeze all by itself, I say, really? When you put water in the freezer, it just doesn't turn into ice all by itself? Yeah, it does. So again, this is a situation where temperature ultimately determines if the reaction or process in this case is spontaneous. So freezing is spontaneous at some lower temperature, lower than 0 degrees Celsius. So anything below 0, water all by itself will turn into ice. Go ahead and take a look on page 591, figure 1521. Kind of shows the same thing we're talking about. So delta G0, find there going up, that's for non-spontaneous processes. So if delta H is positive and delta S maybe is also positive at a certain point, temperature we see there, or delta S negative, doesn't matter what temperature, it's going to be non-spontaneous. So we see plus plus, that process will only have a negative delta G once temperature gets high enough. Conversely, below 0, we got spontaneous processes, so delta H negative, delta S positive. Doesn't matter what temperature, it's always going to be in that spontaneous zone, so to speak. Delta H negative, delta S negative, mostly spontaneous until you reach a certain temperature, and then above that temperature, we see that line moving up, positive slope there, the value becomes more and more positive for delta G. So that's also something important to talk about, magnitude of delta G. So the delta G becoming more positive if temperature increases, or more negative when temperature increases, for example. All right, table at the bottom of the page there just shows some examples. Exothermic processes, increasing, decreasing in entropy, and whether those processes are spontaneous or not, or if they're sometimes spontaneous at a particular temperature. All right, 591 at the bottom there. Mercury sulfide, dark red mineral called cinnabar. Metallic mercury obtained from the roasting of the sulfide in a limited amount of air. Estimate the temperature range in which the standard reaction is product favored. So again, we're trying to find the situation where delta G is negative. So in this case, we're using delta H for the reaction, delta S for the reaction. So take a look at the values. Delta H, negative 238.6 kilojoules per mole, so exothermic. Delta S, positive 36.7 joules per mole Kelvin. So we have minus plus, if you will. So I'm thinking back to this table. So exothermic reaction that increases in entropy. At what temperature will this reaction occur spontaneously? Or in what temperature will the formation of products be favored? All temperatures, any temperature. So the forward reaction, if you will, the reaction as written there, is spontaneous at any temperature. Coincidentally, the reverse reaction, as it says, is non-spontaneous at all temperatures. It will not occur at any temperature. All right, number 115 on page 600, actually. Page 600, number 115, go ahead and do A and B. Pause now. So the reaction in letter A is exothermic and it increases in entropy. Notice the change in entropy is pretty small. So if the temperature increases, what's going to happen to the magnitude of delta G? Well, as T goes up, delta G is going to become more and more negative. The magnitude is going to increase. It's going to be negative always, no matter what the temperature is, but the magnitude will increase as temperature increases. Letter B, same situation. We have an exothermic reaction that increases in entropy. So once again, as T goes up, the magnitude of delta G will also increase. So not the size, delta G goes down, it's like a negative, right? But the magnitude will increase, it'll become more and more negative. Notice that since delta S is greater for letter B than letter A, that the value of delta G will change by more if you increase the temperature of B than A. All right, let's try one more, 119 on page 601. You're asked to estimate the temperature range over which each of the following reactions is spontaneous. So we can do that using delta H and delta S values. So go ahead and pause the video and do that now. All right, so based on the delta H and delta S values, we can predict if the reaction is spontaneous at a lower temperature or higher temperature. So here's what you end up with. And then to calculate at what temperature below will be spontaneous for A and C, or above what temperature for B and D, take delta H divided by delta S. All right, that completes this lesson, this unit. Thanks for watching.